Okay.
So, hello everyone, I'm Alexandre, PhD student at
PhD student
Lip6.
at Lip6.
So sorry for this technical problem.
Technical
So I'm
problem.
pleased
So
here
I'm
to
pleased here to
present the paper that
present
you
the
can
paper that
see
you can
on the
see
screen. So
on the
it's a very
screen. So it's a
long
very
title, so I
long
won't
title, so I won't
read it out
read
loud.
it out loud.
So I choose
So
to present
I
this
chose
paper
to
today
present this
because
paper
it's a
today
very
because
interesting
it's a very
paper because it
interesting paper because
uses
it
a lot of
uses a
techniques
lot
from,
of
I would
techniques
say,
from, I would say,
state-of-the-art in
state-of-the-art
the
in
federated
the
learning,
federated
decentralized or
learning,
not,
decentralized or not,
Byzantine-resilient literature.
Byzantine-resilient
So
literature.
I nice read and
So I nice read and
it
it
will
will
enable me to
enable me
explain a
to
little
explain a
bit
little
of
bit of
some
some
technique
technique
that
that
exists in
exists in
this.
this field. So
So
here
here will be
will be the overview of this presentation. So let's go with an introduction. So I will first, what is reinforcement learning? So there's an agent. This agent can be a robot or whatever. And this agent will, for example, in an environment that can be a maze or a game, a playing field, etc., will do an action. And this action, once he is doing this action, the environment will provide him two things. First, it's a reward, and then another state. So, for example, if he's moving in a maze, he will change its coordinate. And the reward can be, for example, if he is closer to the maze or not, to the exit of the maze or not. And we repeat this loop until multiple times so that the agent can learn to achieve this task, his task, for example, finding the exit of the maze. So here, for example, is an example of a reinforcement learning, I would say, benchmark, which is called linear lander. So normally it should be an animation, but you can see the little robot above the screen. So he's trying normally to land between the two flags. Oops. Oopsie. So what is decentralized reinforcement learning now? So here there are multiple devices, and each of them has a robot or an agent, and they are trying to share between their parameters, which is responsible for the action that they do when they are in a particular state. And here, so they exchange their parameters directly. In our world, so in this paper, some of them might be Byzantine, so that might be malicious. They are tampering with their parameters. And maybe some of you know about multi-agent reinforcement learning. And here it's not we are not talking about multi-agent reinforcement learning because here in a given environment, there's only one agent. So let's talk about the paper. So in this paper, here are I would say the main settings. So they are in a synchronous world. So when a message is sent, the message will be received with a time that is bounded. And they introduce two algorithms. The first one is a centralized approach. So when the robot exchange parameters, they go through a central server first that will do some aggregation and will give I would say aggregated parameters to the central server to the robot back. And the decentralized approach, so the robots are connected between each other directly. In these settings, the topology was complete, so each robot was connected to all the other robots, and they are trying to achieve some task. And yeah, sorry, I forgot. So F here is the number of Byzantine malicious robots that were allowed for the algorithm to be resilient enough. So if N was F was greater than N divided by 2, the Byzantine node will overcome the honest robots. So let's talk about the centralized case, which is the most easiest and will help us to understand the decentralized case. So at each period or at each iteration, there is the choice between two actions based on the result of a Bernoulli trial, so at line 2. So except for the first round where we are in the first, I would say, if, so between line 4 and line 8. So here, each worker agent will do sample trajectories. What does it mean? It will do some kind of simulation based on their own parameters. and they will receive, for example, they will have receive multiple time state action reward, and they do it until the end of n episode, so n learning process. VT is a kind of gradient, or approximated gradient, or temporary gradient, I would say. So it's based on some estimation of the function given by the function g, and which is based on the trajectories that was sampled using their current parameters. And so each agent here, each robot will sample those trajectories, and the central server will aggregate it. And as you can see, the aggregate function is in bold, which is where the Byzantine fault tolerance part of this process. In the other case, so if the binary trial gives the other result, so 0 here, it is a central server that sample trajectories. So based on the central model, and they will build this temporary gradient a little bit differently.
So it's
based on gradient estimation again. So very similar to what was done by the client only. And then they use their previous gradient and estimation of the previous gradient based on the current trajectories. So this line 11 is here to do what they call variance reduction. So it came from another previous paper on reinforcement learning, where their goal was to reduce the variance so that the convergence was faster and better. And then finally, we do a gradient ascent, because here we want to increase the reward that we receive. And yeah, I forgot. So the function that I'm trying to optimize here basically is increasing the reward that they will receive based on their current parameters. So the decentralized algorithm is very similar to the client-server part.
So can I ask a question about
the
previous geometric algorithm one?
Yeah.
So in what sense is this still federated learning, given it's happening at the server? Is it that the information is decentralized, each worker is sending different trajectories?
Yeah, so you see from line 3 or line 8, it is a worker that is doing the optimization part. They're sampling trajectories, and then they compute the gradient. See? But at line 8, the central server will aggregate to the gradient.
Okay.
And it's a line.
But who's doing the learning?
It's
the agent. It depends. Either it is the agent from line 3 to 6. Okay. Or it is the central server based on the parameter that they currently have.
Okay.
So yeah, it depends on the spec. They alternate between two phases. Either it's learning, either it's the agent, or it is the central server. And what was also slightly different is that they do not sample the same number of trajectories. So either it is n for the agent, or it is the central server with b smaller than n. In the decentralized case, so it's very similar. So they also alternate between two actions. So based on the Bernoulli trial. And what is important is that here, the result of the Bernoulli trial should be the same for every node, so that they are synchronized between when they should aggregate and what they aggregate. So at line 5, again, in line 4, they sample trajectories. Yeah.
They told me you should stop your microphone.
Should
mute.
Yeah, forgot because this.
To be better now. So at line 4, we sample trajectories again, and here the number of trajectories that we sample is depending of the Bernoulli trial. So either we sample a lot, or we sample less. And then at line 5, so it is similar to what was done previously. Based on what was sampled, we use different formula to build the temporary gradient. And at line 6, we do aggregation. So what does it mean? It means that here the gradient was broadcast. Every agent broadcasts their gradient, that temporary gradient, and based on this broadcast, every node build a aggregated gradient. And then they apply it at line 7. And finally, at line 8, they do something that they call average agreement. So they broadcast every node broadcasts their parameters. that was a result of the optimization that was based on the optimization on the gradient ascent. And I will explain the bold part, also the bold primitive that gives the Byzantine-resilient part of this algorithm. So here is I would say, literature tree of what was used to achieve Byzantine fault-tolerance decentralized reinforcement learning. So if I have to do a kind of brief summary, CRUM is a state-of-the-art federated learning techniques that it used to filter Byzantine effect. The aggregate part comes from two operations, so based on CRUM and bucketing that I will explain later. An average agreement was something that was think of in the fully decentralized, so without central server. And they introduced two techniques, so either NDA or RBTM, and they introduce two variants, and depending on the settings, so it's asynchronous or synchronous, they have different guarantees with regard to the number of Byzantine. So here, as we are in the synchronous case, what are interesting for us is for f less than n. So what is CRUM? The idea of CRUM is to filter extreme value, to have let's say a value gradient that makes sense in some sort. So the setting in this paper was the data distribution should be IIG. And why we have this requirement? The idea is that if the data distribution is IIG, every node should have the same learning material. They learn the same things, so the gradient should be approximately the same for everyone. So if a gradient is too different, it means that the gradient is probably Byzantine or from a Byzantine node. So they do some assumption with regard to the number of Byzantine. And I will explain how they filter. So for each input xi from x1 to xn, they build the set Si, which is the set of the n minus f minus 2 closest neighbors of xi. And then they compute basically what is, they select the x such as it is the closest to its closest neighbors while trimming for the extreme nodes. So here we select a point that was given. Then a little bit later, some authors propose a techniques to basically make it more interesting in the non-IID case by reducing the variance. And the idea of that is that, well, okay, CRUM works because it's IID, and we can, based on the assumption that it is IID, the variance is minimal or not that big. If we reduce the variance, maybe it will make it more sense to apply CRUM on something that is now less in a set that is has less variance, basically. But here, as you can see, the assumption is that we have an n that should be greater than 4f, so much bigger than the 2f plus 2 than of CRUM, of simple CRUM. So how we achieve that? So the operation that they call bucketing is that you divide your set x1 to xn into multiple smaller sets randomly. And those buckets, what is interesting is that the variance of each bucket is less than the variance if you consider the full inputs, x1 to xn. And then you apply CRUM on the bucket's means. That's why you need much more value. And that's why you need an n that is greater than 4f, because you are applying CRUM on a much smaller set than before. And finally, we'll explain so the average agreement part that was used to aggregate the parameters and not the gradient. So at the latter part of the algorithm in the decentralized variant. So here the setting was, again, collaborative learning. So every node was connected to each other. It's a distance-based technique, again, against Byzantine attacks. And the idea is that here we select a point, an average of a min-max problem. And the data distribution keys were assumed to be non-ID, and the assumption so for f should be less than n. And I will explain to you so the output of the minimum diameter averaging techniques that was used so to filter bad parameters. So as you can see here, we do some mean, and I will explain to you so the max between xg and xk with j and k between in a set S means that here we are computing a diameter of a set. And how we build this set? So we consider a set S that is between 1 and q, 1 and q are integers, and the size or the cardinal of S is q minus f. So here q is at least the number is less or equal to the number of honest nodes in the server, so in the system. So here basically we are considering every set that is of size that is at least less or equal to the size of the honest nodes, and we are computing the smallest diameter of the algorithm of the system, so that we are sure that basically we again filter extreme value. So that's why hence the name of the algorithm. So minimum diameter averaging, and at the end, yeah, we compute so the average of parameters of the set S. So hence the name of the techniques. So here are some results that was presented in the paper. So in the x-axis, it is the number of iterations. And the y-axis, it is the reward that was the cumulative reward. So as you can see, so PHPG is a state-of-the-art algorithm. So on the blue line color. In the orange color, it's the algorithm that I introduced you. So the decentralized reinforcement learning techniques with k equal to 5, so 5 nodes, and again with 13 nodes.
A question?
Yeah.
And each agent is seeing the same distribution of environments in this case?
Yeah, they are studying the same environment. So cardboard or lunar lander, yeah. But what is interesting is that, the reward is greater if they join the collaboration techniques, because basically they put it in common and they merge it. So that's why they learn faster and better than, so it's an incentive basically to join a collaborative learning system where they can share the same, they do achieve the same task, but not with the same environment, kind of the same. And here as a result, when they are considering Byzantine sometimes, so on the blue line, it's a simple reinforcement learning task. So only one node and no malicious. The orange line is as naive adaptation of the previous algorithm, so PSPG, but with more nodes, 13 now. And in green and red line, so it is a algorithm. It's the same. It's a decentralized and Byzantine-resilient algorithm, but with 13 nodes and with a number of Byzantine equal to 3 out of 13, so less than 25%. And as you can see, so on the random action, so I will present the first graph on the left. So random action, here the Byzantine, when they are Byzantine, so the Byzantine node here will do random action based on a state. So as you can see on the green line, the naive adaptation of the normal reinforcement learning problem will suffer from this attack. So at the beginning, they kind of learn something, and then because of the Byzantine action, it decreases. So they don't achieve the normal task, which is here landing between the two flags. And on the large noise problem, so here the Byzantine node will add noise on their agent. So as you can see, they kind of learn to achieve that task, but not as it should with the, I would say, the blue line, which is a kind of baseline. So the normal reinforcement learning with only one node. And while we can see that, for example, in the red line, so the decentralized resilient part kind of still manage to learn successfully the task, and how even outperforms the normal reinforcement problem with only one node. And finally, the last attack was called average zero. So here, the idea of Byzantine node, it was trying to considering the values that was sent by honest nodes. So considering the parameters that was sent by honest nodes, they sent a parameters such as when they do the average between honest and Byzantine, it was equal to 0. So that's why you can see that on the green line that, well, they never managed to learn. Because if here, due to this attack, Byzantine node managed to successfully stop the learning process by basically always sending as 0 parameter 0. While we can see that the red line, so the decentralized variant, outperforms against the normal reinforcement learning problem, even despite being subject to attacks. So yeah, it was a nice read because it involves a lot of techniques in the traditional federated learning settings, even in the decentralized variant, which is even rare. So that's a lot. Thank you.
Your question.
Maybe. I don't have it.
No, but they hear us, so
yeah.
So, in the room.
Is there anything here that's specific to reinforcement learning? I mean, would the same techniques apply equally to other learning settings, or is there something specific? Do you feel, the protection against Byzantine behavior? I mean, that's a problem for any federated learning. So, is there something specific to that protection that's relevant to RL?
Yeah. Okay. Well. Okay. So yeah, I would say not that much. Besides the fact that they, so the PHPG algorithm was an idea, I would say, from the reinforcement learning literature to alternate between two phases and consider the previous gradient. I would say that the contribution of this paper was more like how to make federated learning, I would say, techniques, visual techniques, compatible with the reinforcement learning settings. So, for example, here we filter differently based on if we aggregate gradient or parameters. So I would say, yeah, it's.
So you say the technique is general, but the paper is specifically about
reinforcement learning, because
how to make it specific to
reinforcement learning. Yeah,
okay.
Exactly.
And I have a question of another kind. So when you present the results, if I understood correctly, the blue curve is one agent doing reinforcement learning alone.
Yeah.
So you said, and it's here that you gain in cooperation, and I was wondering, what is the cost of this cooperation? Like, for example, how much information you need to share over the network to achieve this kind of cooperation? I know it's a vague question, but I don't have the sense of how often the model is exchanged, for example, with the central unit or with the other robots. So,
yeah, so that was not, maybe I'm wrong, but in this paper, they didn't do some measurement, but yeah, some operations are definitely costly. So for example, even for Chrome, the complexity is n squared, because just due to the computing, because you compute the distance between a set of a point and the other point of a set. So this computation is quite costly. Yeah, but yet, yes, overhead, I would say in the decentralized part, it shouldn't be that big. But yeah, maybe in a decentralized, fully decentralized, yeah, definitely maybe be more concerning.
Like at the beginning of the algorithm, you showed that you have a binary choice.
Yeah.
So you do one and the other, and then you share with the network, and then you repeat, or you do binary choices.
Yeah, I can show the algorithm again. So, for example, in the centralized, it's decentralized. Oh, Okay, it's centralized. Yeah. So here, it is a server that is doing the random choice of 0 or 1.
Okay.
And based on this, yes, it is the agent.
Based on this, it from
Yeah,
okay.
yeah, or they sample directly from their current parameters.
Yeah, so basically it needs to
Be synchronized. Hence,
and get
aggregate, yeah.
aggregate at every step. Yeah. Thank you.
Yes.
So for the results part,
Yeah.
I was wondering what are the in practice the Byzantine attacks?
Here, for example.
Yes.
Okay, yeah. So here, for example, for the large noise, the Byzantine, they add a lot of noise, the Gaussian noise, to the gradient that they send.
Okay.
Because they just want to tamper the training process, such as every other node fails.
But do the Byzantine workers cooperate?
Yeah, they cooperate here, especially in the average 0. Because, okay, here in the large noise, I mean, the Byzantine could be independent and they send randomly Gaussian, strong Gaussian noise with a lot of range. But in the average 0, yeah, they did cooperate. So they more or less wait to receive all the honest nodes weights. And then they compute the parameters they send parameters that when you average it with the other parameters, honest parameters, yeah, it was 0. So that's why, yeah, this attack is very strong. If you don't consider like any resilient Byzantine resilient techniques with the green line.
So in the first one, they are each dishonest worker puts a random action and sends it.
They send, yeah, so they train when they sample trajectories, they do random action. So yeah.
But so the first one and the second one are not Byzantine attacks.
Yeah, okay, yeah, depending on your definition of Byzantine, yeah, exactly. So
only the third one is
yeah, if you they call it Byzantine, yeah. If you you using the term from the splitted system, yeah, where they corroborate, etc. Yeah. Only the last one is Byzantine attack.
Okay, thank you.
Can you remind me what's the state in lunar lambda? So for Carpol, it's a vector.
Here it was lunar lambda.
But for lunar lambda, is it an image or is it some vector state? I forget. Because I know it has a picture of the lunar lambda, right? But I don't know, is that the state, the image, or is it?
No, it's not. I think it was. I don't remember. I think the state, it depends because there are two settings for lunar lambda, either the continuous or the discrete one.
Okay.
And in this paper, I don't think they precise which one they use. But I think the observation space was between, there was 8 features, I think, in the observation space.
It's a feature vector, it's not the image of the...
I think it was position, etc. Yeah.
Thank you.
Thanks.